Now let's take a look at probability distribution functions, or PDF. A discrete probability distribution function has two characteristics, so you need to make sure that each probability is between 0 and 1 inclusive, and that when you add all of the probabilities up, you total 1. For example, a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 moms, the following information was obtained. Let the uppercase X equal the number of times per week a newborn baby's crying wakes its mother after midnight. So for this example, lowercase x will equal 0, 1, 2, 3, 4, or 5. The probability of x is the probability that uppercase X takes on a value of lowercase x. Why is this a discrete probability distribution function? So there's two reasons. Let's take a look. First, if we look at the table, we have all of our information here. We can see that the probability of a newborn waking its mother 0 times is 2 out of 50. So this is a random sample of 50 moms. So 2 out of 50 said that their newborn baby did not wake them after midnight. 11 out of 50 said the baby woke them 1 time after midnight. 23 out of 50 said the baby woke them 2 times. 9 out of 50 said their baby woke them 3 times. 4 out of 50 said their baby woke them 4 times. And 1 out of 50 said their baby woke them 5 times. So we're trying to decide why this is a discrete probability distribution function. And if we go back, we know that the probabilities each have to be between 0 and 1 inclusive. So if you were to calculate each of these as a decimal, they would all be between 0 and 1. And then the next thing we have to do to verify that it's a PDF is we have to add them all up. The sum of the probabilities has to equal 1. So when we add up all of these probabilities, they do in fact equal 1. So this is a discrete PDF. Here's an example. Suppose Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days 15% of the time, 1 day 4% of the time, and no days 1% of the time. Suppose 1 week is randomly selected. So A says, let uppercase X equal the number of days Nancy, and it's the number of days Nancy attends class per week. X takes on what values? So here we know that X is going to take on the values of 3 for 3 days a week, 2, 1, and 0. I'm actually going to rewrite those in order. And last, suppose 1 week is randomly chosen. Construct a probability distribution table called a PDF table, like the one in the previous example with the babies and moms. The table should have 2 columns labeled P and P of X. What does the P of X column sum to? So let's begin. So we have X and we have P of X. So we know our values of X are 0, 1, 2, and 3. The probability that Nancy is going to attend 0 days is 1%. So I can convert 1% to a decimal because we write our probabilities in decimals. So 0.01. The probability that Nancy is going to attend class 1 day a week is 4%. So 0.04. The probability Nancy is going to attend class 2 days a week is 15%. And lastly, the probability that she will attend class 3 days a week is 80%, or 0.8. We can do a 0. So what does the probability of X column sum to? That means what happens when you add all of that together? So let's grab our calculator here. 0.01 plus 0.04 plus 0.15 plus 0.8 equals. So when we add all that together, we get a total of 1, which is fantastic because that is one of the constraints of it being a PDF.